So what we're going to do here is look at z-scores. What z-scores let us do is compare unlike events. So things that operate completely differently, what we could do is compare which was more likely or which was less likely. But some things we have to take into account is where did we expect to be, which is the idea of the mean, so where are we centered, and then what's our standard deviation? That gives us an idea of how far away from the mean that we are. So even if the two events are quite different, what we can do is compare them, and we use the standard deviation as a ruler. So we want to see how many standard deviations each event is away from the mean. So this is the idea of a z-score. It calculates how many standard deviations away we are from the mean. So what we're going to do is use that same information for Portland. So Portland rainfall, and let's just draw a little normal curve here. So with Portland rainfall, again, we expect to be at 40, and then we had our standard deviation of 8. So seeing this number line, we get an idea of where we expect to be. But then what we want to do is compare to Chicago wind speed. So let's see what the curve for Chicago wind speed looks like. So they tell us the average wind speed is 10 miles per hour. So if we have our normal distribution, that's the center of the curve, with a standard deviation of 2. So 12, 14, and then go below. So we get these two curves. Chicago wind speed works with a normal curve centered at 10 with a standard deviation of 2. Portland rainfall, normal, centered at 40, standard deviation of 8. So you can see it's two completely different curves. I mean, comparing rainfall and wind speed, they have different units to them, different expected values, different spread of values. So here we're going to look at, suppose annual rainfall was only 24 inches in Portland, and Chicago had an average wind speed of 13. Which of these events was more extraordinary? And at this point, just comparing 24 with 13 doesn't do anything, because this is representing 24 inches of rain in Portland compared to 13-mile-per-hour winds in Chicago, and there's just no comparing at this point. What we want to do is compare how do they land within their curves. And this is where our z-score comes through. So in terms of which is more extraordinary, what we're really asking is which event is further from the mean. The wording of extraordinary, it doesn't really matter being above average or below average, it's just far away from the mean. Sometimes questions will ask like which of these were further above average, and then we'd be wanting to look for these specific values. But in this case, it's just distance from the mean, which is further. So this is our z-score formula. Notice it's using population notation here. You will sometimes see it with sample notation. It's just in this section we have population values. This is the idea of our z-score formula. Our x value, so that's some data value that's given. We're taking some data value, and then you subtract away the mean, or our expected value. And then we want to divide by standard deviations. So what we're doing here, in the numerator, taking a data value minus a mean, we're finding the distance away from the mean, distance away from average. And then, like we were saying, we want to see how many standard deviations each event is away from the mean. So the numerator takes care of just distance away from the mean. But then to put in terms of how many standard deviations, we divide it by our units of standard deviations to create our same units there. So let's see how this works for this example here. So 24 inches of rain, that's going to be our X value. So for Portland, what we want to do is see how far is this output of 24 away from our mean in terms of standard deviations. And actually from our picture up here, we can already get an idea of what should come out, because 24 is right there. And that's landing nicely at 2 standard deviations below the mean. But let's see how that comes out in this formula. So we take our data value of 24 and we look at the distance away from our mean, which is 40. So we have our distance away from mean, and then what we want to do is put in terms of how many standard deviations. So with that, we divide by our units of standard deviations, which is 8. So when we calculate this, it gives us -2. So getting this -2 out, it tells us rainfall of 24 inches in Portland is 2 standard deviations. So we get our distance of 2 standard deviations, and then because it's negative, that means it's below average. So we get this idea of if we're above or below average, and distance in terms of standard deviations. With Chicago wind speed, so with a wind speed of 13 miles per hour, and now this is our X value for this scenario. So 13 is landing right here. So we can see, let's see, 12 is 1 standard deviation away, and then this is about halfway. So we can imagine is from this calculation, we should be getting 1.5 standards, and this one's landing above average. So let's see how that comes out here. So with our z-score, we find that distance away from the mean, which is 10, and then we want to divide by our standard deviations, which in this case is units of 2. And this calculation will give us 1.5. So this is telling us that wind speed of 13 miles per hour in Chicago is 1.5 standard deviations. And then in this case, because it's positive, that's telling us it's above average. So these values, now we have a way of comparing them. We have a way of putting them on the same number line. So in calculating these z-scores, if your z-score is negative, that means it's below average, whatever your data value is. If your z-score is positive, then it was above average. If your z-score comes out to be exactly 0, what that would mean is in the numerator, those numbers are exactly the same, so like we'd have 40 minus 40, which would mean the data value we're checking is exactly equal to the mean. So this one, results that are exactly the mean, or exactly average. So that's some interpretation for your z-score there. So with these, now what we could do is create this number line in terms of standard deviations away from the mean. And what we saw is, for Portland, we landed out here at 2 standard deviations below, and then for Chicago, we were 1.5 standard deviations above. And if we're looking for which event is just further from the mean, well, as we said, if we had a z-score of 0, this is the idea of being equal to the mean here. By the way, this has a distance of 2, so Portland was further away from average, so Portland had the more extraordinary event. Again, positive and negative didn't matter here. If they wanted to see like which event was more above average, it would have been Chicago, because that's the only one that is above average, with Portland being below average. So be careful with the wording there of what event they're looking for. So this number line here starts mapping our z-scores, in that z-score being exactly equal to the mean, which in terms of our data, if we have our bell-shaped curves, this is where we expect to land. And then we expect mostly to be within one deviation away, and that's what these are saying. This is one standard deviation above average, one standard deviation below average, and then 2 standard deviations above, 2 standard deviations below. What we start getting is a number line that actually works together with these bell-shaped curves here. It's just using a different scale. But how we talk about this line is very similar to what we talk about above, in that most of our values land here, and then as we get further away from the mean, things become less likely, and we can start seeing and describing is our bell-shaped curve. And this right, so it comes from standardizing into z-scores. Doesn't change the shape of the distribution, so we're still going to have our bell-shaped curve. The center becomes 0, because that's where we expect to be. It's the idea of being exactly equal to the mean. And then since we're moving in units of standard deviations, that becomes 1. So if we jump down here to our bell-shaped idea of 0 in the middle, standard deviation above, 2 standard deviations above 3, and then 1 standard deviation below, 2 standard deviations below, so on and so forth. But the idea is, if we go back to how we drew our curve for the rainfall, is that we can translate this into a standard normal curve, with 40 being the equivalent of 0, 48 being the equivalent of 1, 2, 3, -1, -2, -3. It's just that these numbers down here are z-scores, whereas the numbers up above here are x values. But in terms of this being our mean and standard deviation, this is how they're equivalent to each other. So that's where, when we had that x value of 24, it had an equivalent score of -2. So we get out these two curves. And what you'll notice in GeoGebra and any other technology that you use, whenever you jump into the technology, this is where they start off with. And it's because if you hear about those tables in the back of the book and looking up calculations using the z-tables, it's all based on this distribution here, because we can always change it to this distribution. It's just what's nice now is with technology and GeoGebra, we don't always have to use this curve, and we don't need to use those tables, thank goodness. So this is kind of our standard form, and notice it's how z-scores are distributed, and it's a mean of 0, standard deviation of 1, because that's how our center and spread are going to come out. So something to be careful of here, when you see normal distribution model, that just means a normal curve with some mean, some standard deviation. When you say standard normal model, it's a normal curve, mean of 0, standard deviation of 1 every single time. And how those values are found is using our calculations for z-scores. So let's do one more example, comparing two different events. So we have an incoming freshman, took their placement exams for French and mathematics. In French, they scored an 82, and let's start collecting some information. French and math. So in French, they saw a score of 82, so that would be our x value. That's kind of the single data value we want to look at. And then in math, they got a score of 86. For the French exam, overall, there's a mean of 72 and a standard deviation of 8. Whereas with math, there's a mean of 68, standard deviation of 12. And on which exam did she do paired with the other freshmen? In terms of doing better, we want positive z-scores here. We want z to be more than 0 to represent the idea of being above average. So this is a case where if we have a negative number coming through, we don't want to use that. So let's see, our z-score for French, we would be taking that x value of 82 minus the mean divided by our standard deviation of 8, and that should give us a z-score of 1.25. And then for math, we take our data value of 86 minus our mean of 68 divided by a standard deviation of 12, and that's going to give us 1.5. So in terms of which is further above average, and again, I mean, we can go with that this one's just larger. If you think about that number line, this is landing further above the mean of 0. So this one is going to be more extraordinary. So she did better on the math exam. But again, at the beginning of this, we can't just compare the scores of 82 and 86 because they behave differently. Like with the French exam, a higher score is expected with less deviation away from that mean, whereas with the math score, a lower score is expected, but there's a lot of deviation. So we have to take all of these factors into it in order to compare the two values.